Section 10.4 is a multiple regression. And the multiple regression equation is that it expresses a linear relationship between a response variable y and two or more predictive variables x sub 1, x sub 2, all the way up to x sub k, where k is the number of predictive variables. The general form of the multiple regression equation, then, obtained from the sample data is y hat is equal to b sub 0 plus b sub 1 times x sub 1 plus b sub 2 times x sub 2 all the way up to b sub k times x sub k, and you're adding all those. The coefficients b sub 0, b sub 1, b sub 2 all the way up to b sub k are sample statistics to estimate the corresponding population parameters, beta sub 0, beta sub 1, beta sub 2 all the way up to beta sub k. And to find the multiple regression line, the requirement is to, for any specific set of x values, the regression equation is associated with a random error, and we assume a random error, this is epsilon. We assume that such errors are normally distributed with a mean of 0 and a standard deviation of sigma, and that the random errors are independent. The multiple regression equation found from the sample data, then, is y hat is equal to b sub 0 plus b sub 1 times x sub 1 plus b sub 2 times x sub 2 all the way up to b sub k times x sub k. And the multiple regression equation found from the population data, then, is beta sub y is equal to beta sub 0 plus beta sub 1 times x sub 1 plus beta sub 2 times x sub 2 all the way up to beta sub k times x sub k. So let's say, for example, we look at the dataset 1 body data dataset, which includes the heights in centimeters, waist circumference in centimeters, weights in kilograms, from a sample of 153 males. We'll find the multiple regression equation in which the response variable y is the weight of a male and the predictive variables are the height and waist circumference of the male. The actual equation that we could find that would be that y hat is equal to negative 149 plus 0.769 x sub 1 plus 1.01 x sub 2. We could also write it with all the variable names inside of it if it's easier to realize what goes where. We would have weight with the hat above it since it's predicted is equal to negative 149 plus 0.769 times the height plus 1.01 times the waist circumference, which I'll just denote as waist. The r squared and adjusted r squared, so coefficient determination and adjusted coefficient determination. There's a flaw in the multiple coefficient determination, the r squared value. The more variables that are included, the higher the coefficient determination actually is, which is an unfortunate flaw with that. The adjusted coefficient determination, so adjusted r squared, is the multiple coefficient determination r squared modified. It's modified to account for the number of variables and the sample size, which is why you would always have different values. And the adjusted r squared, we would take 1 minus n minus 1 divided by n minus 1 and n minus 1 divided by n minus k plus 1 times 1 minus r squared. This is a measure of how well the multiple regression equation sits, how well that multiple regression equation fits the sample data. As an overall hypothesis test, though, we could run the hypothesis test of the null hypothesis, where beta 1 is equal to beta 2 all the way up to beta k, is equal to 0, and the alternative is that at least one of those betas is not 0. The rejection of the null hypothesis indicates that the regression equation is significant, and failure to reject the null hypothesis indicates that the regression equation is not significant. Individual p-values are given for each coefficient as well. Each hypothesis test would be the null hypothesis is where the beta sub k is equal to 0. Beta sub k is equal to 0. Alternative is that beta sub k is not 0. So this would be the slope is not significant versus significant. This allows us to choose the best multiple regression equation, not just the equation with the most variables. The rejection of the null hypothesis indicates that the slope or the coefficient is significant. Failure to reject the null hypothesis indicates that the slope or coefficient is not significant. And in order to find the best multiple regression equation, we first used common sense and practical considerations to include or exclude variables. Exclude irrelevant variables or variables that, for example, measure the same thing. Consider the p-value, select an equation having overall significance, also known as a low p-value. Consider equations with high values of adjusted R-squared, and try to include only a few variables. We want to try to include relatively few predictor variables as well, since again that impacts the regular coefficient determination. We want to select an equation having a value of adjusted R-squared with this property. If an additional predictor variable is included, the value of adjusted R-squared does not increase very much. For a particular number of predictor variables, we want to select the equation with the largest value of adjusted R-squared. And in excluding predictor variables that do not have much of an effect on the response variable, it might be helpful to first find the linear correlation coefficient for each pair of variables being considered. If two predictor variables have a very high linear correlation coefficient, which is called multicollinearity, there is no need to include them both. We want to exclude the variable with the lowest adjusted R-squared. So for example, dataset 7 foot and height includes the age, foot length, shoe print length, shoe size, and height for each of the 40 different subjects. Using those sample data, find the regression equation that is best for predicting height. Is the best regression equation a good equation for predicting height? Well, due to the what we want, there's a total of 15 combinations. This table down here just says 5 of them. But we want to start excluding some things. Alright, the first thing we want to exclude is age, because this is supposed to be a data set here on criminals, using the foot and height values of these, of the different criminals. And let's face it, criminals tend not to give out their age unless, they get arrested and all that. But age tends to be something that is not really given too much. So not given. As such, since there's a chance that it's not given, we probably should not be including age. The second thing we could get rid of is the shoe size. Getting rid of the shoe size, this is because it is a rounded form of the foot length. Rounded foot length. And because they both measure the same thing, it's best to get rid of one of them. And here, the foot length appears to be the one with the best R-squared value, right? That's 0.7041 with a p-value of 0. Of all the ones down here, that foot length appears to be the highest one. But, as we could also see on here, if we tried to start including other things, right, if we include the shoe print length as along with the foot length, note how the adjusted R squared goes up, but not by much. And then using all the variables, it goes up even more. Again, not that much. And as you could see, it doesn't really impact it that much. So because of that, just the foot length is indeed the best value. Although, based upon this as well, the shoe print length one, depending on what you're looking for, it depends what's actually given. But the best particular equation that we could get from this would be, let me write it here, that the predictive variable height is equal to 64.1 plus 4.29 times that foot length, since it's the best. It's the best model from this. Let me know if you have any questions or concerns. Thank you.